And good evening. Today I'm going to give a presentation on our topic, two-stage preprocessing for license recognition. And this research mainly proposes a non-scanning license recognition system, which cooperate with insurance agency to automatically identify vehicle license and then quickly apply for insurance online. Now this is the outline. I will start from the introduction. The digitization of the financial and insurance industry these days has driven the need for recognition of documents, and the cost of manual identification is high, so the need for automatic text recognition increased. All current automatic text recognition methods require scanning or positioning by apps. So we propose a non-scanned vehicle license recognition system and develop a program to generate the synthetic vehicle license images. In the end, we propose a series of methods to improve the performance. And the mainstream research is divided into two categories: detection and recognition. Therefore, related work will also be divided into two parts: text detection and text recognition. And CDPN is a model designed for text detection. The core of CDPN is not to detect all the text fields at once, since the text is usually fat and short. In text recognition, the left and the right side are often cut off. So CDPN detects a string of bounding boxes and merges them into a complete text area. Segling has similar concept to CDPN. Segling detects parts of the text on different layers in different CN networks and links them all in the end. The author of EAST argues that cutting and merging the text is slow and complex, so EAST directly detects the 4 vertex of the text area, which makes the process faster. After positioning the text, the computer needs to know what text is in the image, and this is what text recognition does. CRNN is a network designed for text recognition. Traditionally, we cut the text. If we don't cut it well, it can't recognize it correctly. But CRNN doesn't cut the words. It uses CNN and LSTM to recognize the text. ASTER is another kind of network of text recognition. What's special is that he proposed a correction deformation network before recognition, and correct the deformed text into normal image, which greatly improved the recognition rate. Regarding our design, we still divide it into text detection and text recognition. And we will talk about the problems with text recognition on non-scanning license. And the first one is difficulties in data collection and distorted images and high precision requirements. And the last one is background noise. And this is the architecture of our system. And the green boxes are our implementations, and the red boxes are using third-party software. Before discussing the two networks of the text detection, we will talk about data acquisition. There are two stages in our text recognition, and these data are used to train a model for correcting the deformation of the line. We only need the information on the left, so we just mark the left side like the red bounding box in the slide. And the data was difficult to collect, and we just gave 25. In these 3 photos, you can see that the anti-counterfeiting totems are all different. Because the information is sensitive, this information is difficult to collect. So we also use the trick of data augmentation. And so they are origin, rotate, zoom, noise, blur, hue, shades, and then transform twice. And in theory, we can obtain an infinite number of images through data augmentation. However, the text in each license is still only from 25 real vehicle license images. If we generate too many images with only data augmentation, the dataset will lack diversity and may lead to model overfitting. Therefore, we only augment each dataset to contain 300 images. And clearly, 300 images is still far from enough to train a detection model. And typically, for a deep learning model to generalize well, the training set size should be in the range of 10,000. And therefore, we enlarge the dataset by synthesizing fake vehicle license images. And these are some examples. And this is an example of a lot of noise in the license, because we hope that the locating network can also detect well when the text is blocked. And let's talk about solve the problem of overfitting. Because the anti-counterfeiting totem of the synthetic fake data is the same as the arrangement of the license frame. And in this way, the model cannot generalize well to real data. So we use the threshold binarization method to remove the anti-counterfeiting totem in the background. And the first stage is rectification network. Rectification network is improved using exception network. This slide shows how rectification network corrects distorted license images. After preprocessed rectification and finally prospective transformation, a rectified image is obtained, and the text distortion has been corrected. Therefore, the accuracy of subsequent text recognition can be improved. And the second stage is locating network. Locating network is also improved using exception network. This slide shows how the rectification network positions the columns in the license and cut the column image. After preprocessed locating, the final crops gets a series of fields images. And after the positioning is complete, each column image which has been cut can be sent to the text recognition model to recognize the text in it. Then we cut each column on the license, and these column images will be sent to the text recognition and recognize the text in the field's images as editable text. Before text recognition, we proposed a denoise network to eliminate the anti-counterfeiting totem in the license. And before talking about denoise network, here we will first introduce the training data of denoise network. Because the purpose of this denoise is to remove the background totem of the license. And here are some examples. So we also generated our own training data. And let's take a look at A and B. B is the network output. It is text images with no noise in the background. And A is the text of B plus a lot of background noise. And let's take a look at L and K. L is also a text image with a simple background and no noise. K not only has background noise, but also frame-line interference. And by using this data, it allows the noise to also remove borders across text. And let's talk about the noise network. Since the input size of the denoise network is fixed, but the image size of the column after positioning is different, therefore we split the fields imaged into a series of fixed size images. And there is overlap in each image, so that information about the boundary is preserved. And then send it to the noise network. You can see that there is a frame on the original images, but it was removed after going through the network. And after the noise network completes background removal, the field image can then be sent to the text recognizer to recognize the text in it. And here we use some commercial text recognition software. And the first one is Google Vision OCR. And Google Vision OCR is a paid service and can recognize text without removing the background, even when there exists a high level of noise. And the next one is Tesseract OCR. Tesseract OCR can only work on text image whose background noise is removed, and is open source and free software, and can be retrained and fine-tuned. And this making Tesseract OCR more flexible. And after the text recognition software recognizes the text in the license, there are usually some errors in these identification results. So we came up with post-processing to correct this problem. And we propose 3 tricks to fix unreasonable results. And the first one is dictionary. A dictionary is created for some specific field. If the recognition result of these fields are not in the dictionary, the result will be marked as recognition error. And the second one is type checking. Some fields can only contain numbers. If Chinese or English characters are recognized in these fields, we will mark this as a recognition error. And the last one is spatial character removal. Text is usually located in the center of the image, and the starting, end, or ending of the recognition text may contain spaces and line breaks. And the spaces and line breaks are removed in the recognition text. And let's talk about performance. And our experimental result will divide into 2 parts: 2-stage detection and text recognition. And it is important to know that all models are trained using synthetic fake data. In order to ensure the robustness of the system, part of the performance test is to use real data for verification. And all models are implemented using Keras on TensorFlow. And let's talk about our performance evaluation metrics. And the definition of IOU can be seen on the right. Suppose the green one is ground truth, and the Levenstein distance is the difference between 2 sequences. And that is the recognition accuracy of text recognition under different allowable values. And in the case where IOU is 0.5, that is under the standard of the field of object detection, precision recall F1 reached 0.99, while in IOU it is 0.7, precision recall F1 were 0.9 and 0.99 and 0.95. Unless recall always remain 0.99, this means that there will be no license is not detected. So the text detection system performs very well. and it will not cause the bottleneck of subsequent text recognition. And this is a very common example, license with a little crease, but our text detection can cover it well. And here we can note that some of the text exceeds the fields. But we also consider this situation when we're generating fake data, so our text detection can perform well. And since the insurance agency only needs the 4 most important fields to successfully apply for insurance, and they are license number, owner name, vehicle brand, and factory date. And here we will take 4 columns that only identify the vehicle license, which will be represented by 4F in the table. In addition, we also provide the text recognition accuracy of all 20 fields, and which will be represented by 20F in the graph. And we also want to understand the impact of the denoise post-processing we design. And this table is the result we made with Google Vision OCR as text recognizer. In the case where the recognition result is exactly the same as the ground truth and the Levenstein distance is 0, 4F plus denoise plus post-processing can reach 0.989, and pure 4F can only reach 0.73. So our method has been improved from 0.73 to 0.89, and 20F plus denoise plus post-processing can reach 0.81. In the case where the recognition result is exactly the same as the ground truth, Levenstein distance is 0. All models perform poorly. And the table shows that 4F plus denoise plus post-processing and its Levenstein distance is 0.01, and 4F is 0.0. However, when Levenstein distance is 1, from 4F to 4F plus denoise plus post-processing, the accuracy raised to 0.18. And our conclusion is we propose a 2-stage text recognition system, which can be used for text recognition of non-scanned vehicle license images. And in the first stage, the rectification network can effectively correct the deformation of the vehicle license images. In the second stage, the locating network can accurately locate the position of the text. In addition, we propose a denoise network to solve the shortcoming of the non-scanned vehicle license image. The experiment results show that our system can effectively improve the text recognition accuracy for vehicle license images. In the future, we will try to minimize the deep learning models to reduce the running time. And this is the end of my presentation.